I will speak on this topic of deep learning. Um, my background is, as you see, in what's called computer vision. And computer vision is essentially very much about trying to write software that automatically recognizes things in images, like here is a cat, here is a dog, here is a bicycle, and things like that. And the reason why I am here talking about deep learning is because that is exactly the field where this method, or it's a sort of method of machine learning, has actually made a tremendous progress in the last few years. But it's not the only field, so I will come back to that a little bit. But so I will tell you the sort of story, mainly the story about deep learning in computer vision and how it actually achieved its results in recognizing images. But I will also talk about the possible futures and things like that. Okay, so in this field of computer vision, back in 2006, people started trying, actually, when digital cameras became sort of so common, and basically when you got cameras in mobile phone and everything like that, you could collect lots of images. It was so easy. Suddenly it got so easy to collect lots of image data compared to before, when you had analog cameras, you had to take the film, and digitize it, put it in the computer. It was really a tremendous difference. So people started building large data sets. And also, this data sets, as you know, if you're if you have some background in machine learning, you know that data is what you use in order to actually achieve some programming, some efficient programming. So data is essential. But also, the data is essential in order to evaluate what the program does, okay? So we started collecting these data sets of buses, cars, ducks, bicycles, whatever. And then there was a contest every year saying that, okay, now you can submit your software, you can train on this data set, which is a subset of this, and then we will run your software and see how it performs in terms of able to find the cars and find the bicycles, et cetera, et cetera. So that was a contest every year, and that was a winner every year, okay? And if you look back in those days from 2007 and onwards, typically the winner in these contests would sort of be a little better than last year, but only a few percent, essentially. You could see how it gradually improved over time, basically, okay? And actually, you could see also by 2012, it was almost like, oh, these curves are actually leveling off. Because if you look at human performance on this, you would go up to 98, 99%, basically. So this is very subhuman performance. That's the thing. Okay. But then in 2012, and from 2012, something has happened, and this is what happened. That the curves suddenly started to turn around and go the other way, basically. And instead of improving about 2-3% every year, you had an improvement about 10-15% every year, okay? And the reason for that was known as deep learning, okay? So I will give you a very brief, a very simple overview of what deep learning is. It's not really from a mathematics, I'm not going into the deep mathematics of this. I will show you exactly the, so this is, deep learning has improved dramatically, not only in vision, but also in speech recognition, which is sort of similar problem when you sort of automatically translate when someone is speaking and you translate it into words. This is what enables you to speak to your computers, for instance, okay? So those programs, software programs that existed before deep learning, they have been more or less replaced, I think, now by deep learning algorithms in that field, by Microsoft and Google and all these guys. Okay. And also, for instance, in automatic translation of language. So that is a whole, and I will come back to this, and also there's a whole range of applications that I will come back to. So basically what the deep learning does, it tries to extract patterns and information that previous algorithms weren't able to do, okay? That's, okay. And of course, it has had a dramatic impact, especially in industry. So every major computer company, you might really, especially in the US and also in China, of course, are now setting up special labs for actually doing deep learning or deep learning artificial intelligence and things like that. So that's where the impact has actually been. Okay. So what is the reason for this? What is the reason? Why was it so successful? Well, there are three main reasons that we always come back to. It's the fact that back about around 2008 or something like that, there was at Stanford University, they started to actually collecting even larger data sets, about 15 million images that were annotated. Basically, they had students, paying students a very low sum of money for actually saying, put a box around the fox, put the box around the airplane, etc., okay? So that was sort of crowdsourcing in order to get an annotated data set. And this data set was critical because now you have 50 million images, 1,000 different object categories, okay? No, we had never done anything like that before. This was a large scaling up of the data sets that we had, okay? There was another reason. Back about that time, NVIDIA started producing these graphical processing units, basically for doing computer graphics. It turns out that when you want to do deep learning, the mathematical operations, which are basically convolutions, linear operations on data, is essentially what these things do, are very good at. So that's what they do. The deep learning people discovered these are very efficient, and that's what you should be using now for deep learning. Okay, and the third thing was that deep learning was based on the traditional, if you remember, back in the 1980s, the people started working with what's known as neural networks, which was essentially, they claimed it was a way to mimic how the brain works and things. Now, there was lots of excitement about that because suddenly they were able to actually do more complex learning than they had done before. But essentially, there were no big results back then. There was lots of hype about the neural networks back in the 80s. And basically, and eventually it turned out they were no better than anything else, any other machine learning method, like support vector machines or boosting algorithms or whatever, basically. But there was a subset of the neural network guys who persisted in actually saying that, okay, neural networks is the thing to do, basically. So what they did was they scaled up these networks and put even more layers into these things, basically, and even more parameters, okay? And that was, and the reason why no one, and of course they could do that because now they had the computing power, and now they had the data sets actually to put into these, okay? And another thing is, okay, by going up to something like 60 million parameters to be set in this network by training, basically, you would think that you would actually run into problems compared to the previous ones where maybe contained only 1,000 parameters, something like that. But it turns out that this scaling, and so people were worried because what you do when you train these networks is you try to solve an optimization problem, a very nonlinear, non-convex optimization problem in general. And people said, oh, it will not work because you will end up in a local minima, especially if you make them bigger. And that's what happened initially. But eventually, it turns out that it was found that by increasing the size, by scaling the networks, you actually do not run into problems. You solve the problem because what happens is, of course, you get a lot of local minima, but they are all very good. They are all just as good as the global minima. That's the thing, and that's what people. And that's a fascinating fact, actually, by itself. Okay. So what is, just very briefly, this is basically the mathematics I will do. So when you do machine learning, of course, what you have data, and you have sort of, to each data point, you have a label. It could, in this case, we say it's just a number or something like that. X is a number, Y is a number, Y is a function of X, and you try to find that function by using the data. For instance, a linear function, which is, of course, this is what you do when you try to fit points, line to a point, set of points, okay? And And in order to do that, if your points are noisy, you cannot find a single line, but you can find the best line by minimizing the error, the approximation error of the lines to the data points, basically. That's what you do. Okay, so in this case, the model is A, B, and the data is X and Y. Okay. And if you see this as a machine learning is basically, this is essentially what machine learning is all about. You take a subset of your data, you fit the line, you fit your model to that data, and then you see how well it works to the whole set, to the whole data set. That is what machine learning is about. And that is essentially what deep learning does. But instead of two parameters, instead of having just one parameter in, you have a whole vector in, okay? And that vector could be the pixels in the image. The first element in the vector is the first pixel, and then the last element is the last pixel, okay? So you put in, you have a vector instead of scalar, and then basically you try, but essentially the idea is the same thing. So you take, if you take pictures like that, you will get different vectors for different objects, basically. So that's the idea. So they will be in different points of the space. Here, the space is only 2-dimensional. But think about it, in practice, it's 10,000 dimensions. That's what you have. But the basic idea is the same. You try to find a function around the cat points that is basically has a high value where there's a cat and a low value where there's no cat. That's what you do. So it's a 0-1 thing, basically. Same thing for dog, basically. And same thing for all the 1,000 categories. That's what you do, basically. But essentially, it's the same thing as finding the parameters for the straight line. Because what you try to do now is you try to find the parameters of a deep network that, given an image, that you put in lots of images. Instead of having just lots of points, you have put lots of images, and you try to find these functions that gives you a high value for cats in the first node and 0 values for the other nodes. If there's a cat image, if there's a dog image, the second node in the output should be high, all the others should be 0. That's what you try to do, but basically the basic idea is the same thing. You try to find lots of parameters that minimizes the error, basically. So it's the same, it's essentially just a least squares problem, optimization problem that you saw. But instead of having 2 parameters as in the straight line, you have now 60 million parameters. That is the main difference, okay? Okay. So what is in more detail, when you talk about these networks, so let's say this is a simple network, then you have just a 2-dimensional input. And what you do is, in these networks, of course, you have to, when you want to compute these functions that we are talking about, you have to do it in an efficient way. And one efficient way is to, of course, the most efficient computation you can do is linear, just linear summations like this, okay? And this is what these nodes do, the first layer in these nodes. And then you can put these outputs of the first y1 and y2 into a nonlinearity like this. Okay, which basically tells you that if the value of y is negative, the output is 0. If the value is positive, the output is the same thing as the input. It's the most simple nonlinearity you can ever have, basically. But this makes all the difference because, and then you can, of course, put even more larger input vectors, but they're essentially the same idea. You have convolution layers, you do linear summation, and then you put through the nonlinearity, and that's it, and you get the output. And you can, of course, have even more layers. In here you have, this is for the sort of standard way of depicting it, that you have sort of convolutional layer first, nonlinearity, and then another convolutional layer, and a nonlinearity. So basically, what you end up with functions at the output that have high values when there is a cat. If there is a cat image, you have a high value on the first node, etc. As I told you before. Okay, okay. So that's how you. That's how you train these things. And of course, in practice, what they look like is something like this. Okay, you can see that these are sort of the dimensions of these these layers and how many nodes they have, etc. Okay, okay. This is what Google came up with in 2014. It's about 20 layers, and then in 2015, Microsoft double that into 150 layers, okay? And I think the latest versions are now using about 1,000 layers. So that's an interesting fact by itself. You actually grow these things every year. They get bigger and bigger, and you get better and better performance. Or at least I know until 2015, you actually got better performance. That's the interesting thing. And if you look at the results of these on this ImageNet data set, if you put the human in front of that, the humans will actually, according to what I say, will actually have only about 5% error in the classification of looking at these images. Okay, and here you can see how the error of ImageNet actually goes down, and in 2015. Microsoft claimed to actually have better than human performance. But these images are quite simple because you have the object filling almost the whole image. Okay, it's more difficult if the object is not sort of localized in the image, if you have to find it also, basically. Okay, so that's summarizing this. What you're doing is basically you're trying to solve what's known as the regression problem, by finding the value of 60 million parameters that gives you, for a certain input, the correct output, basically. But you try to do it, you formulate it as an optimization problem, okay? And the question is, of course, why is this so much better than anything we had before, okay? This is the problem. We don't really know that. And that's also the interesting thing about it. We don't have a really good explanation why suddenly, because before you had deep learning, people were sort of training, and people were training for visual recognition by focusing like on one category at a time. They tried to make sort of a car recognizer, basically, and tried only car images, and then they tried it. And then they used sort of all other images as a sort of negative class and tried to discriminate between cars and non-cars, basically. But the funny thing is that if you try to learn everything together, all 1,000 objects together, it gets better. So obviously, there is something that was missing by focusing on only one class and trying to optimize for that. There was something missing there, because it seems that cars, horses, dogs, houses seem to have things in common that helped, that sort of, by training on all things together, they actually seem to help each other, okay, in some way, which we don't really understand right now, okay? But it's by having more data together, it actually gets better. It's like there is more sharing of features in these objects than we really thought before. And you have to remember that before this, people were sort of trying to find sort of excellent features that could be used in order to build classifiers and things like that. And people were working for 40 years. And it took after they started, it took just about 1 or 2 years, basically, before they were all beaten by these things. That's the funny thing. But it seems that the key to the whole thing was sort of the amount, this big data set, learning all the classes at the same time. That is as far as we understand it right now. But it's an interesting problem by itself. Why do these things actually work so well? Okay, what is it really that makes these things work? But it's a really, really complex problem, because what we have is basically a solution. We have a solution to a problem by just doing a big optimization, and by just looking. Now we have the problem of actually finding what all these 60 million parameters or all these 5 million nodes basically are doing by looking at the activities at the node. You know, this is like we are in the same position as the neuroscientist going into the brain and trying to find what is this neuron in the brain doing and things like that. But we have no better tools than the neuroscientists to actually analyze this. This is the funny thing. Or we have, but so far we haven't come up with anything real better. But the whole thing is interesting because it could be that in traditional engineering, of course, when you put a complex system together, you know exactly what each piece is doing, okay? And it has a relation to all other pieces and things like that, and you know exactly why they fit together, okay? But here, basically, it's like the whole network is working as a unit. It's very difficult to decompose the network this thing is doing this and this thing is doing this. Although there has been attempts to do that, okay? Because you can look at the network, and say, oh, what makes this node actually most active? Well, sometimes it's a face, and sometimes it's just a diagonal line or something. And in general, the earlier in the networks, the lower complex, then you have lower complex features like diagonal lines or whatever. But the higher you go up, you go all the way. Then you start seeing sort of real objects or parts of objects and things like that. I don't know. This is a sort of application that we are sort of building. You're sort of abstracting out the information in a in a higher way, basically. But still, it's not really satisfying. We don't, because what you know when you try to do these things, what you do is, in order to find out what this node is actually doing. Then you have to try essentially all images possible. But of course, they have only tried a subset of those things. So we don't know. There could be other images where this node is active also. It could have multi-modes and things like that. And we don't really know that because it's so complex, basically. Okay. You can also, this is an extreme example when you look at a certain node and you say, which image, and then you try to really optimize the image that activates this node, basically, okay? And then you come up with things like this. And people have interpreted this as, this is what you see when you hallucinate things, okay? So it's basically, if you activate your brain, this is the image that you will actually perceive, basically, okay? I don't know. There's lots of speculation about this, actually, but let's not take it too seriously, at least not right now, basically. That's the thing. Okay, so, well, what can we do now that we couldn't do? Because of deep learning. Well, of course, you have seen this thing about autonomous cars and self-driving cars and things like that. And in order to actually drive cars, it's good if you have vision, basically. In order to find like pedestrians and bicycles and other cars and things like that. So that is, of course, where lots of major companies are trying to work right now, basically. Okay, it's a heavy competition. Even Volvo is also involved in this, of course. Another field which was not able to do before is basically you can now more or less get verbal descriptions out of images. You can actually train a network to actually give you a text description of what is going on in the user. So you provide lots of images and lots of text. Have people give you text descriptions. So you provide lots of training data for this, okay? But then you train the network. So the network notes the relation between the input image and that output text, basically, and learns a network that sort of achieves this mapping. And then you can sort of automatically annotate images like that, okay? So this is a very interesting interaction between vision and language. And I'll come back to language. Language is also very, very interesting, basic potential. It has a tremendous potential in this field, I think. You can also, of course, you can sort of try to abstract. You can actually teach networks you can teach network by putting in lots of images of different artists here, like Van Gogh and I think and other famous painters. You can sort of try to learn the style of these artists in the networks, and then you can input an image and see what would they have painted and things like that. So that's also another interesting side effect of this, I would say. Okay. Not only vision and image recognition. All these deep learning things have had a large impact in field of speech recognition. Actually, I think it started actually before the vision part. So now you're down to very few % errors in automatic speech recognition. And if you try to summarize, basically, you have image, speech, language translation, natural language processing. I will come back to that a little bit more. Bioinformatics, people have taken long sequences of DNA, for instance, and they have been able to train networks to find mutations that are sort of lethal or cancerous or something like that, okay? That were not able to do before. And people are, a big field in this right now is, of course, the medical field. Okay, I'll talk a little bit about that. Basically, trying to take in medical data, blood pressure, any kind of measurement that you can make of your body, lab tests, and also eventually personal DNA, things like that, and see if you can learn the health status of the person or the potential dangers for this specific person given this data. Okay, so this is a big field that people are really trying to work in right now. And then you might have seen these things about playing automatic chess playing. You can actually teach programs to play chess with deep learning, but also you remember in March or April, something like that, you have this Chinese game of Go, which is considered as 10 times or very much more difficult than chess. It beat the world champion in chess, basically. And what you do there is you have the game board, the board. The computer looks at the board and maps the positions on the board into a strategy, okay? And that mapping is achieved by having the whole thing play games by itself, against itself, essentially. You create lots of training data, basically. I'm just noting success and failure, okay? This is known as something called reinforcement learning. And this is, of course, also the same thing when you want to do robotics. In robotics grasping, robotics navigation, basically you take an image and then you want a strategy for actually grasping the object in the image, okay? That's the same thing. Google had I think a dozen robots standing a whole week or something like that, just looking at the images, trying to grasp, noting success and failure, and then training them to actually grasp things. It's like babies teaching to grasp things like that by success and failure. Okay, so but they are basically using the deep learning algorithms for actually achieving that. That's the interesting thing. So. This is the most interesting thing about deep learning. It's not just vision, it's not just speech, it's essentially any domain where you have lots of data. That's where these things are being tried. And of course, I might forget there's lots of other things. Like I know that people in law enforcement, but lawyers and things like that, trying to understand legal argument, trying to get what is the correct judgment here in this case, and given other cases that have a similar case and things like that. And of course, in economics, I mean, that's also a big field by itself. Okay, so you can probably make this list twice as large actually if you just continue. So that's it. Okay, and. Yeah, so in general, what you are trying to do is, for the image case, it seems that what you have is an input space, and the images they contain they lie on some very, very thin manifold in this high-dimensional input space, okay? And then you try to find a mapping from this input space into some output space. And this is sort of the general, as you see, it's sort of going from this straight line where you had X and Y, now you have lots of one input space and another output space, basically. But it's essentially the same problem, basically, going from one input data manifold to some output, which is not necessarily data, but basically when you have humans, it could be a human decision. So essentially any activity involving a decision by human based on experience could be modeled by these networks. That is the interesting, by just providing the input data and the decisions that were made by people, okay? So this could be, for instance, in health, in having medical doctors, lots of medical information about, for instance, and building up these networks. That could be one. But essentially any, and that's what makes it so general, any human experience could be put into this, okay? Yeah, so this is like in the medical field, okay? Yeah. And of course, the big thing is if the input is not sort of numerical data, but what about if it's language? I mean, lots of our decisions, lots of human decision is not based on numerical data. It's based on actually text. It's based on language, basically. You are being told something. You read something, okay? What do I understand from this? Okay, can you actually automate the process of human understanding with this? Okay, that is sort of the really open domain problem. And the interesting thing about this is, the first thing you can do is try to map language into a high-dimensional space, just like an image. And this is what people have done. It's called embedding words. So that means that similar words or similar connecting words, they lie on some kind of data manifold like this. But basically, you make a vector out of a word by noting how the context in which it occurs, how close it is to other words, like France and Italy probably very often occur together and things like that. So they occur very close together in this high-dimensional vector space. Okay, and it turns out if you do the same thing for capitals, you will end up. So basically you can put words, and that means you can put sentences into high-dimensional space. Everything becomes these vectors, and then suddenly you can start using these convolutional nets or deep learning in the same way as you use images. That's the exciting thing, and this is what the language people are trying to do right now, because this is very, and this is of course probably the most potentially important field. Okay, because if you have a text, you can ask. What we can do is we can tell what the text is all about. Is this about football? Is this about whatever? Whatever. That's quite easy. It's quite easy to do today. You could produce summaries of text, just shorten the text basically. We can do that today. You can actually compute the sentiment of is this text praising or is it critical, like a movie review or something like that. That we can also do automatically today. But what we cannot do, we cannot sort of say, I put in a text and then the output, I have understood this from the text, basically. This is what we cannot do, okay? So what would be ideally the automatic text understanding, because that would allow us, if you have that, then you would basically have any human could interact with very complex databases, and of course, the great thing about this would be like, it would be like you could communicate with databases, data sets in the same way as you as you communicate with humans, basically. Okay, so the ideal thing is you could make teachers, individualized teachers here, which is the only pedagogy that actually works, basically, when the pupil can ask questions every third second or something like that. That is the only thing probably that works, and that would allow this to have individualized teachers for every person. So language understanding is really the important field in the future for this, and lots of work is going into this. I know especially in the US, in the big companies and things like that. Okay, thank you very much.